Hello everyone. We are given a system governed by the following differential equations: dx1 by dt equals x2 minus x1 and dx2 by dt equals x1 minus x2. The initial conditions are such that x1 of 0 is less than x2 of 0 is less than infinity. We are asked to find the nature of the final values of the states. To know more about the concepts used to solve this problem, kindly refer the NPTEL Control Engineering course Week 12, Lecture 6 by Professor Vishwanath Talasila of Ramaiah Institute of Technology, Bangalore. The zero input response of an LTI system x dot equals ax is x of t equals e raised to at x naught, where x of t is the state vector, a is the state matrix, e raised to at is the state transition matrix, and x naught is the initial state vector. The state transition matrix can be computed as e raised to at equals Laplace inverse of Si minus A the whole inverse. So in this question, we are given a system governed by the equation dx1 by dt equals x2 of t minus x1 of t and dx2 by dt equals x1 of t minus x2 of t. It is given that the initial conditions, that is x1 of 0 is finite, that is less than infinity, and x2 of 0 is also finite. So we are asked to find the nature of the final value of the system, that is x1f equals limit t tending to infinity x1 of t and x2f is equal to limit t tending to infinity x2 of t. So let us write the state space form for this system. So you have x1 dot and x2 dot equals the A matrix. So the A matrix you can obtain from these equations. So you have the coefficient of x1 as -1 and that of x2 as 1. In the second equation, the coefficients are 1 and -1. So now this is x1 of t, x2 of t. So this is the A matrix. Now this system is of the form x dot equals ax. So the solution for this differential equation is x of t equals e raised to at x naught, where x naught is the initial state vector. So now let us find e raised to at. So e raised to at is called the state transition matrix. So you can obtain it by Laplace inverse of Si minus A the whole inverse. So this is the easiest way to obtain the state transition matrix. So now Si minus A the whole inverse is inverse of s plus 1 minus 1 minus 1 and s plus 1. So when you compute the inverse, this will be equal to 1 by s times s plus 2, that is the determinant, times the adjoint, which is s plus 1, s plus 1, 1 and 1. So now you can take the Laplace inverse, which you can find by partial fractions. So you will get e raised to at as half of 1 plus e raised to minus 2t, 1 minus e raised to minus 2t. Again, diagonally they are the same. 1 minus e raised to minus 2t and 1 plus e raised to minus 2t. So now we can compute the solution. So that is x of t equals e raised to at x naught. So which means x1 of t, x2 of t equals e raised to at is this matrix, that is half times the initial state vector, that is x1 of 0 and x2 of 0. So now the final values can be computed as x1f, x2f equals limit t tending to infinity x1 of t, x2 of t. So I can substitute this here. So that is equal to limit t tending to infinity half of this matrix times the initial state vector x1 naught and x2 naught. So now as limit t tends to infinity, this exponential terms will go to 0. So what is remaining is this is equal to half of, there is a matrix with all ones in it, times the initial state vector x1 naught, x2 naught. So which means x1f, that is the final value of the first state vector, is half of x10 plus x20, and the final value of the second state vector is half of x10 plus x20. Now since we know both the initial conditions are finite, we have this term is a finite quantity and this term is also a finite quantity. So which means we have x1f equals x2f less than infinity. So looking back at the options, we find that the correct option is option C, x1f equals x2f is less than infinity. Thank you.